the x-intercepts. Now, technically, we need to call these the p-intercepts, right? Because our variable is p, not x. But it's okay if you say x-intercepts because we understand what you mean, right? How do we do it, though? Set what to 0? The numerator. Okay, set the top equal to 0 and solve for p, right? So p is what? 0. Okay. Good. That's our p-intercept, or x-intercept. 2, find the vertical asymptotes. How do we do that? Denominator to 0. Okay, 1 minus p equals 0. Right? And now I would just add p to both sides. Add p, add p, add p, and you get 1 equals p, which is the same as saying p equals 1, right? 1 equals p is p equals 1. We good? What's the next step? Horizontal. I'm going to erase this. I'll put it back up in a minute. Horizontal. And that, you look at the degree of the numerator and denominator. What's the degree of the numerator? 1. What's the degree of denominator? 1 as well. So now what you do is they're equal. So this is case 3, right? So the numerator's degree equals the denominator's degree. So we're going to let, this is case 3. So y equals what? The leading coefficient of the top. What's the leading coefficient of the top one? 50. 50 over the leading coefficient on the bottom. Be careful here. Negative 1. There's a 1 here in front, right? But do you see the negative in front? You got to grab that as well. So negative 1. So this is negative 50, like that. Y'all good? Okay. We are going to continue by doing what now? Sketching it, right? Let's sketch this. So for the sketch, I have an x-intercept or p-intercept at 0, right? Right there at 0. Remembering that this is p, which represented the percentage, and this is our money, right, in millions. What else do I need to put on my graph? Vertical asymptote, where's that at? At 1. I have a vertical asymptote at 1. Now watch, I'm going to put my 1 out here. 1. Okay. Now, horizontal asymptote at negative 50. That's way down there, isn't it? That's way, way down there. So I'm going to do this. I'm just going to put it right here, negative 50. And this is a horizontal, so I only draw it at the edges, right? I only draw it out here, way out here, and then over here. You'll see we're doing exactly the same procedure, right? Now I want to sketch it, right? I want to sketch it. So I need test points. What are my test points? How many do I need? Test points, I need 3, right? Need 3. Right, because I had one p-intercept and I had 1 vertical asymptote, so that's 2, so 1 more than that's 3. All right, where do y'all want me to grab them from? Negative 1, okay, that works. That's something to the left of that. Now, 0.5 or 0.75, something in the middle of these, right? 0.5, let's go with that. And then something to the right of 1, 2. I need to plug those in to my function and see what I get. Pardon?
What do we normally do? Or we just use the negative?
You want positive, negative? Yeah, we could do that. Now, I'm not actually going to go through this step. I'm just going to tell you what happens. So when I take the C function and I plug in negative 1, I'm going to get a negative answer. When I take the half and plug it in, I'm going to get a positive answer. And when I take the 2 and plug it in, I'm going to get a negative answer. Not showing my work, just saying if you plug those numbers in, that's what would happen, okay? So let's go draw the graph, or let's go plot these points. When I'm at -1, I put a dot below, right? When I'm at 0.5 or a half, I go up, right? I used 1/2 over here instead of 0.5. Is that all right, everyone? And then when I'm at 2, I'm down somewhere, right? Like that. Yeah, I'm going to start drawing. You all ready? Here, this way, flatten to the magnet. What about to the right? Connect. So it's just going to connect here, and then what's going to happen to the right here? It has to go up like that, right? And then this point to the left, what happens? Goes down. Can't go up, right? No x-intercept. And then to the right, flattens out towards here. Okay. Y'all understand? So I told you that this is a function that gives you the cost of taking out a certain percentage of pollution from the lake, right? What's the smallest percentage we could take out from the lake? 1. Well, 1 would represent 100%, right? Remember, as a percentage, 1 would be 100%. Smaller. Smaller. Wouldn't the extreme be that we don't take out anything, right? That'd be nothing, right? 0. How much would that cost us? How much should that cost us?
0.
Nothing. Look at our graph. At 0, how much is it costing us? 0, right? Nothing. Nothing. It costs us nothing at 0, right? Now, does it make any sense to say we're taking out a negative percentage? No. So in reality, in the real world, this graph, we don't even want to look over here at all because it doesn't make sense to use a negative percentage. Now, everything between 0 and 1 represents from 0% all the way to 100%, right? And then once you get past 1, again, even though we have a graph, it doesn't make sense in the real world, right? So this graph is irrelevant to us this way. Understand? This function is only relevant between here and here. And does it behave the way you think it would behave? At 0%, it costs us nothing. We don't want to take any pollution out. That's free. We do it every day. Shit, we throw stuff in there all the time, right? We don't care. But the more you want to take out, the more expensive it's going to get, right? And theoretically, you can't ever get 100% out. It's impossible to get 100% out. Because as soon as you've got 100% out, there's a bird, flies over and takes a shit, and it's no longer completely clean. It's impossible to get it 100%, right? So the cost is infinite to get to 100%. In the real world, we need functions that behave like this to model situations. Now, that situation is just something you can connect to, but in the real world, there are things that behave like this. And so this is just an illustration of why rational functions are important in the real world, because there's no line you can draw that will do that. Linear functions don't behave like this, right? Parabolas don't do this either. You may say, well, wait a minute, that looks kind of like a parabola, right? Like part of a parabola. You might argue that's part of a parabola, but remember with parabolas, quadratic functions, right? The idea is that this goes up, but it continues moving over this way. There's no barriers ever on parabolas. It just keeps going up and up and up and over. What type of function has a barrier that we can't cross? Rational functions. All right? Okay. You will see a problem like this at some point down the road. All right? I'm just letting you know. You'll see something like this, probably on the final. Pardon me? If we kill the birds? Well, then there will be something else that goes in. Yeah, all of them. Well, yeah. We could just get rid of, just drain the lake, and then all the pollution's gone, right? Because there's no lake. It was just a thought exercise. Okay, we're ready to switch gears. We're going to move into our next type of function now. And I think before I do this one, before I actually tell you what it is, I'm going to do a little exercise here. Let's see if I have a piece of paper I can sacrifice. Who has a piece of paper? Someone want to donate? Oh, here we go. I've got one. There we go. Okay, we're going to play a little game here. It's not going to be fun, but it's a game. All right, so what I'm going to do is I'm going to make a table over here. And over here, I'm going to put the number of folds that I put in this paper. And then on this, I'm going to put the number of rectangles that we see. All right, number of folds and number of rectangles. Yes? We're not talking about rational functions yet, but I don't want to tell you what we're talking about yet. I just wanted to think about something. I kind of did. If you remember the list, it's the next one on the list. Okay, so here's a piece of paper, right? I have not folded it. How many rectangles do you see? One. Okay. 0, 1. Now, I'm going to fold it one time in half. Okay, right in half. And then what I'm going to do is where it folded, I'm going to draw a line. And now, how many rectangles do you see? 3? Where? Well, the one was the big one. And now I folded it and opened it again, and you have 2. Don't count the original one on top. Yeah. So 2 new ones, right? 2. So 1, you're doing like a rolling sum. Okay, so there we go. 1 fold, 2 rectangles, right? Now I'm going to fold it again. So fold it where I folded it before. I'm going to fold it one more time. And I'm going to open it up, and how many are we going to see? 4? You don't think 4? Yeah? It's not a trick. I'm just asking you. You're trying to guess. So open it up. There's the new fold line. And now we see 17. No, we see 4. I'm giving you a hard time. We see 4, right? So 2 folds, 4. All right. 3 folds. 6. 6. 9. 2.75. 8. 4 across, 2 down. 4 times 2, there's 8 of them, right? It's not quite maybe, well, some people said 6, which is a very common response. We didn't get 6 though, we got 8. Let me go again. 4 times. What do you think? 16? What else makes sense? 12? Let's just see. Let's just do it and open it up. So 4 across, 4 down, 16. What's happening here? Do y'all see a pattern? It's okay. So I'm hearing a couple of things, and they're all correct. They're doubling every time, right? They're doubling every time, which means it's multiplying by 2 each time. And then I also heard powers of 2. These are all powers of 2. All right. So let me see. If I did it again, let me do it one more time. 5th fold. Open it up. I should see how many? 32. Okay. By the way, bring your calculators from now on, please. Bring your calculators to class. So here's the fold. I believe there's 8 across the top. and there's 4 down the side. 8 times 4 is 32. So there are 32 rectangles here, which is double that, right? If you take 16 and multiply times 2, you get 32. So 5 folds is 32. So each time you take that number, multiply by 2, you get 2. Multiply that by 2, you get 4. Multiply that by 2, you get 8. Multiply that by 2, you get 16, right? So we should expect that if we fold it, 6 times, that we get 64, right? Just double that, and I'm not going to do it, but that's what would happen. There's actually, have y'all ever seen a show called Mythbusters? It was popular in the 90s, late 90s, early 2000s or something. And they basically like take these myths and they see if they're true or not. And there's a myth that you can only fold a piece of paper 7 times, I think was the myth. That you can only get a piece of paper and fold it 7 times. After that, it's like physically impossible to do. Like it gets too hard. Yeah, so what they did is they got this huge roll of paper and they took it out into like an aircraft hangar, right? And this huge roll of paper that was like the size of a football field. And they used, and it was like real thin paper, like Bible paper, like, you know what I mean? Like, and then they folded it over and folded it over, and they used a forklift and a steamroller, like to flatten it, you know? And I think they got 13 folds. So there is a physical limit, but it's not 7, right? It's more than 7. And I'm going to try and explain why there is a limit, all right? Maybe we can convince ourselves that there has to be some limit to it, how many folds you can actually get. So let me ask you this. If you understand this pattern, can everyone tell me what 7 folds would get us? 128, right? 7 folds. I'm going to continue the table over here. So 7 folds would give us 128. So let me ask you, if we could fold it 13 times, how many rectangles would we see? Well, right now what you would have to do is next find out what 8 is, right? By multiplying that by 2. And then you have to find out 9 folds, multiply that by 2, then 10, then 11, then 12, then 13. Then you'd have my answer, wouldn't you? Right? But that's inefficient. That's not an efficient way to do this. So what we want to see is there a function where I feed it this number and it spits out that number? That's what we want to know. Is there a function that does that? And you can sit here and play with all the functions we've studied up to this point, and you're not going to find one. There's not a line that does this, a linear function. There's not a parabola that does this. There's not a polynomial function that does this. And there's not a rational function that does this. This requires a special category of functions, which is the one we want to study now. So to understand how the function works, let me point something out on all of these, which was brought up a second ago. These are all powers of 2, which means this. 2 is 2 to the first power. 4 is 2 squared, right? 2 times 2. 8 is 2 times 2 times 2 again, right? So 2 cubed. 16 is 2 times 2 times 2 times 2. That's 2 to the 4th power, and so on and so forth, right? And do y'all notice something about that power and how it's exactly this number, right? This number, the input that we plug into the function, if we just put that input right there on the power of the 2, then that will give us our answer. What about, does it work for this first one? It would have to be 2 to what power if this is going to work? 2 to the 0, right? If this pattern works, then this has to be 2 to the 0, right? And somewhere before you got to me in some other class, hopefully you were told that if you take any number a and you raise it to the 0, the answer is 1. So any number raised to the 0 is 1. Y'all got this? So if I wanted to know this right here, what's 13 folds, how many rectangles do I get? Then I need to do 2 raised to the 13th power, right? So if you have a calculator, I'd like for you to do that, please. You got it? How did you type it in? How did you do the 2 to the 13th? So you use that little key? Okay, so on your calculators, there's this key that looks like this. It's called the caret key. And what it does is it raises things to powers. So when you type this into your calculator, you'll do 2, and then you'll hit that caret key, and then you'll do 13, and then you'll hit, equals, or what is it, enter? What does it say down there? Enter. Okay. 2 raised to the 13, enter, and you should get the answer, which is what? 8,192. 8,192. Rectangles. If we could fold that piece of paper 13 times, if we could, and I open it up, we should expect to see 8,192. All right, just out of curiosity, what if I folded it 20 times? Get your calculator. This is 2 raised to the 20th power, which is? Just read the numbers out to me. 1048576. That's it? Okay. How many rectangles is that? 1,048,576 rectangles. So let's think about this for a moment. Nobody has textbooks anymore, huh? Does anybody here have a book with them?
Yeah.
You do?
Just a book.
Yeah, like can I see it? Okay, so I don't need it. Everyone see this book right here? It's what, maybe about an inch thick? Yeah, maybe about an inch, maybe a little more. Let's just say an inch thick, right? How many pages is that book? Okay, 500 pages. 1 inch, 500 pages. Do you all agree that when I take this page, right, it's 1 page thick, right? When I fold it once, it's now 2 pages thick. When I fold it a second time, how many pages thick is it? 4. When I fold it again, how many pages? 8. It's the 4 that I had before, and now another 4, right? So it's the same thing, right? So I could have said number of folds, pages thick. To fold it 13 times means it's equivalent to the thickness of a book that's 8,192 pages thick, right? That's 500 pages?
Yeah.
So it would take about 16 of those books. That's how big it would be. 16 of those books stacked up is how thick that page would be. But that's physically impossible because this one piece of paper isn't even that tall. You see, like, how am I going to get 16 books deep? Does that make sense? How can this be 16 books thick? I don't have any more physical material anymore. And just imagine if you tried to get to 20 folds. That's how thick the book would be. 1 million pages long. 1 million pages, right? This is growing extremely fast, right? Like each step up we're doubling, and it's just growing and growing from here to here. Look at that huge jump, right? Look at that huge jump. So these functions, let's actually define what this function is. All right. This is the function. F of x equals, for this particular example, it's always going to be 2 on the bottom, right? And we're raising it to the x power. Notice the placement of the x there. Bless you. Notice the placement of the x. Where is the x? Up in the exponent. We call that the exponent, right? It's up there. Don't confuse that with this. This is not, bless you, this is not this. These are two different things, right? This one, the base is the variable. The 2 power always stays the same. The power is held, the variable is down here. This is a parabola. This is a parabola. We studied this already. So this is not that. This is special. It's like they switched places. This has a name. This is called an exponential function of base 2. exponential function of base 2. This is one example of an exponential function, just a single example. I'm going to talk about a few more things with this, and then I'm going to show you some other examples, but there's a few things I want to point out here that are kind of off topic, on topic. Does anyone recognize these numbers? Let me see. I don't know. Like 8, 16, 32, 64, 128. Anyone know what the next number would have been in this list? 256. Okay, next one would be 512. Anyone recognize these numbers? You ever see those in the real world anywhere? Where? Where have you seen those? I mean, not like, you know, yes, of course, maybe you've seen them, but there's something in particular I'm trying to get you to make a connection with. Oh. Y'all own a phone? When you buy a phone, they ask you about how much storage you want, right? And what are the common numbers that they give you? Like 128, 256, right? Those numbers are not arbitrary. Those numbers are based on this idea because all computers, okay, all computers, the way a computer works, and I think we talked about this before, is that all a computer knows is on and off. There either is an electrical signal or there's not an electrical signal. That's all a computer knows. Yes or no, on or off, 0 or 1. That's all a computer understands. And so everything relies on two pieces of information, on or off. That's called binary, and binary is a base 2 number system. So everything in a computer is base 2, So all the numbers within a computer are going to be increments that are like this, which is why when you're asked for storage, they don't tell you, hey, you know, you could do 128 or you can do 150 or 250. No, you'll never see 150 because it's just not the way storage works. Everything is in blocks of powers of 2. Understand? Okay. That's the first thing that has to do with this powers of 2. The other thing is, are y'all familiar with the March Madness tournament that just finished? No? So I know not everyone here is into sports and stuff, but there's a tournament that takes place every March where the college basketball men's teams play each other in a tournament, and then they have the women's also. The standard tournament is 64 teams, okay? So you have 64 teams. Do y'all know why it's not 65? It has to be even, it has to break down. Okay, so, all right, so 64 teams, and what happens is let's say team 1 plays team 2, right? And they see who wins, and that winner goes here, right? And then team 3 plays team 4, and then they play, and that winner goes here. Then those two teams play each other, and then it keeps going. They break down until they get to the final 2. They play for the championship, right? So in the very beginning of the tournament, they list out all these teams. All 64 games are set. All 64 teams are placed, and there will be how many games? Are you okay? Okay, all right. I know, I got you. There are 64 teams, so how many games would be played that first round? If there are 64 teams, 32, right? So there's going to be 32. So in round one, there's 32 games. Got it? And then in round 2, you have 32 teams left now, right? So there will be how many games in round 2? 16, and then in round 3, 8 games. Round 4, 4 games. Round 5 is the championship because that's 2 games left. Wait, no. I think I lost track of myself, but you get the idea, right? 5 and 4. So at the very beginning of the tournament, they publish this, what they call the bracket, okay? And then it's free to anyone in the world. You can go onto websites and you can fill out this, and you can try and predict who you think is going to win every game all the way to the champion, all right? And then you submit that before the tournament starts. You submit it, and if you get your bracket correct, they will give you millions of dollars. Is $1 million? You don't even have to pay to enter the challenge. You can, it's free, okay? Now, let's see why they're willing to like take the gamble on letting people fill that out for free. How hard is it to get these all right? So now look, I understand that team 1 and team 2, when they play, they usually put the best versus the worst. All right, so there's a pretty good chance that like Kansas is going to beat UTSA, right? Like if that's what happened in that first round, right? So there's a way that you could try and figure out what's going to happen, but let's just say we don't care. I want to know how many different brackets are possible. How many different ways can you fill this out? So we can actually figure this out. So look, for this game, how many different options do we have to put here? There's 2 options. For this game, 2 options. This game, 2 options. How many games? 32 games. I have 2 options 32 times. That's 2 raised to the 32. That's how many different ways you can just fill out the first round, okay? Then you have the next round, right? The next round, you now have down to 16 games, right? And there's 2 to the 16 different ways to do that. So you take that and multiply that times 2 to the 16. Now, the next round, there's 8 games, and there's 2 to the 8 power ways to do that. And then 2 to the 4, then 2 to the 2, and then you get to the championship game, 2 to the 1. That means there's only, once you get to the championship game, there's only 2 ways to choose that. So whenever you have this, and you want to figure out what it is, what you can do is just add these numbers up. So if you get on your calculator, add those up. This and this is 48, 56, 63. So someone on their calculator do 2 to the 63 power, and give me a second. 2 to the 63 power. Who's going to do it?
I don't know how to read this.
You know how to read it? Well, just tell me what it says.
It says 9.2.
9.2.
Bajillion numbers.
Okay.
10 to the power of 18.
10 to the power of 18. Okay, so what this means on your calculator is that it's 9.2, but you got to move that decimal point 18 places to the right. 18 places. So if I take this 9, it was 0.2. If I move that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right there, and put zeros here. Now, it wasn't zeros, right? There were numbers in there, but who cares? This is so freaking big, I don't even care. I'll just take the 2 out, too. Okay, what in the heck number is this? All right, like, let me get rid of all this.
People have actually won this.
No, nobody has ever won it. No, nobody has ever won it. Nobody has ever, somebody got to the second round, but no one's ever had the first 2 rounds correct. Yeah. Somebody a year